We interact with artificial intelligence through a series of chat windows and text responses. While it feels fast, this interaction model relies on a sequence of manual triggers that creates a persistent overhead for the user. This is the prompt and wait model. You give the AI an instruction, it generates a response, and then it goes dormant. It functions as a reactive encyclopedia, requiring your initiative to take every subsequent step. Because the system requires manual supervision for every individual action, the speed of your workflow is strictly limited by how fast you can verify the output and type the next command. The human operator becomes the primary constraint in the system. Scaling past this requires a shift in how we employ the technology. We are moving away from using AI to produce static content and toward building systems that make independent decisions. To operate at digital scale, we must move beyond passive chatbots and build autonomous agents, software engineered to act on our behalf. Transforming a passive language model into an autonomous agent requires constructing a cognitive framework. This provides the structure necessary for the AI to navigate toward a defined objective. This framework diagram shows the transformation. At the center is the foundation model, wrapped in external layers designed for autonomous behavior. These layers provide specific capabilities. To work independently, the system requires modules for planning goals, tool use functions, and state persistence. Integrating these structural modules replaces human supervision with engineered autonomy. The agent no longer waits for a prompt to proceed. It follows its own internal logic. A digital brain without a past cannot sustain a workflow. Standard AI models are constrained by a lack of memory, forbidding context once a session ends. A unified memory system addresses this. This architecture manages information across two timelines. A working memory handles immediate context, while long-term memory builds a persistent knowledge base. The agent curates this flow, determining what details to discard, what to update, and what high-value nodes to permanently store based on utility. Without this ability to track its state, an agent cannot maintain coherence over long periods. Memory is the prerequisite for executing complex, multi-step workflows. Reasoning is only half of the requirement. For an agent to be useful, its internal logic must be coupled with the ability to execute actions through external digital tools. In the reflection loop, the agent perceives its environment, plans a task, and acts. If an action fails, it enters the reflection phase, evaluating the outcome, identifying the error, and automatically taking corrective action to generate a successful result. This cycle is the defining engine of autonomy. It removes the need for manual intervention when the system encounters a technical roadblock. Forcing a single general-purpose AI to manage a complex project often leads to errors. The cognitive load becomes too great for one model to handle reliably. Instead, complex goals are decomposed and delegated to a team of specialized agents. Each agent is assigned a narrow, role-specific task within the broader architecture. These specialized agents orchestrate their work, with one agent handling retrieval, while another focuses on validation. This reduces the chance of hallucination and ensures high precision for each subtask. This division of labor achieves results that exceed the capabilities of any individual model, providing a scalable way to solve organizational objectives. This leads us to the autonomy paradox. As we give AI systems more independence, we must engineer more sophisticated boundaries to control them. Allowing agents to interact with external tools creates a gap in accountability. Without a defined scope, an autonomous agent could execute unintended actions that compromise security or data integrity. We must shift from constant oversight to delegated authority. Agents must operate within a verifiable scope, where they can prove their permissions while remaining identifiable as distinct actors in the network. Safety and ethical governance serve as the architectural foundation for autonomous agents, preventing behavioral drift in open environments. We enforce this through semantic telemetry and anomaly detection. These governance layers continuously monitor the system to ensure the agent's actions remain aligned with the original human intent. The result is an integrated engine executing human intent with high reliability at scale. By combining memory, reflection, and specialization, we move beyond simple automation. The transition is clear. Move from writing prompts for static answers to architecting systems for autonomous action.